Hello guys, welcome back to MJ School of Mining and Geology. In today's lesson, we are dealing with the X-ray diffraction principles. We're going to be looking at how the X-ray diffraction machine operates and specifically looking into the Bragg's law. All right, so please don't forget to like, share, comment, and subscribe. And then, but above all, don't forget to hit the notification button below so that you get notified once we upload new content. All right. So, without any further waste of time, let me take you through the principle of X-ray diffraction. So, you'd agree with me that we have what you call an atom, and so we have what we call an atom, and the atom, it's made up of the nucleus, all right, wherein we've got protons and neutrons. We've got protons and neutrons within this nucleus, all right. So this is the nucleus. We've got protons and neutrons, and surrounding that, we've got electrons. We've got electrons over here, all right. So now, these electrons or these atoms, they have what we call a plane. All right. So these electrons, these atoms, they've got what we call a plane. Then we call it an atomic planes. So the atomic planes of crystals cause an incident beam of an X-ray to interfere with one another as they leave the crystal. All right. And then this phenomenon, it's what you call an X-ray diffraction. So that is to say, if the X-ray tube giving us the beam of X-ray. Now, these X-ray, they would be incident into the atom. Okay, so the plane, the atomic plane, would now diffract these um, um, these rays. All right. So it is this X-ray diffraction. It's a rapid analytical technique. Okay, primarily used for the phase identification of a crystalline material and can provide information on unit cell dimensions. All right. So this diagram over here is just to make you visualize that if these black dots or gray dots, they are atoms, and then with what you call the planes. And then, of course, we're gonna look at this space over here. We call it distance d. So when we're gonna be looking straight into the Bragg's law, we're gonna be looking at this distant d between the atomic between the atomic planes. All right. So please keep this in mind: the distance d between the atomic planes. So the diffraction, it happens right here on the atomic planes. All right. So the crystal planes are defined as some imaginary planes inside a crystal in which large concentration of atoms are present. So if we're to imagine this, imagine we having what you call an X-ray tube. We're having what you call an X-ray tube. So this X-ray tube, it gives us what you call an incident X-rays. All right. But now the moment the X-ray tube, it provides us with the X-ray beams. So we say they will be collimated. They are collimated X-ray beam. So that when we say something is collimated X-ray beam, it means an X-ray beam that has been made to travel in parallel lines. Can you now see? It's collimated because now these X-ray beams, they've been made to travel in parallel lines with the rays not spreading out as they move. They are parallel to one another. They do not spread out as they move. Now, this means the beam stays narrow. The beam stays narrow and focused over a long distance. All right. Now, collimating the X-ray beam is very important in experiments like X-ray diffraction because it helps to precisely target the sample and produce a clear, accurate results. So these X-ray beams, they need to be collimated, and then they are focused, okay, and they're parallel to one another, targeting the sample. All right. So when we take the sample, remember the X-ray samples, they're in the form of they're in powdered form. All right, they're in powdered form. Now, when these rays they interact with the atom, all right. Now there happens what you call um, 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 a diffraction. All right. So if we can check, let's say, let me extend this a bit. Let me extend that a bit. All right. So we always say this is the interference, no, the incident, sorry. So we say the angle between the incident and the diffraction is what you call the 2 theta, all right? And then this one is what you call the theta, all right? The incident, or the what you call the Bragg's angle, okay? Bragg's angle. Okay, so you must understand now that these diffractions, they would now interfere. All right, so these diffracted rays, when they interfere, let's say they are in alignment, now they cause what you call the constructive interference, and this constructive interference will be detected by what we call a detector. Then this detector would now it's connected to the computer, and then you will see this the intensity against it will be at the 2 theta angle and versus the intensity. All right, now you'd see these things over at the computer, and then now that's how the people they use these graphs to understand the crystalline structure of the particular minerals. All right. So yeah. So that is the principle of what we call the X-ray diffraction. All right. So this technique is very important in many disciplines. All right. So without any further waste of time, let's understand the components. All right. So the main components are the X-ray tube, the sample holder. Let me do this. All right. So the main, we can check over here. We have got this one. We say it's an X-ray tube. And then we've got this one over here is what you call a detector. And then we've got somewhere here. That's what we call where we put as a homogenized, a powdered sample, all right, within a sample holder. All right. And then in one of our videos, we've explained how we prepare the XRD. Okay, XRD sample, the powdered form. All right. So please, you are more than welcome. If you haven't yet visited the video, you are more than welcome to go into the MJ School of Mining and Geology YouTube channel, and then you shall find that video on X-ray diffraction sample preparation. All right. So now, what I want to bring to your attention is the X-ray, all right? The X-ray tube, this one, all right? The X-ray tube is the part of this machine that generates the X-rays, all right? Whether X-ray are a type of high energy light. These are the type of high energy light. All right, so the X-rays are high energy light, and then they're being produced by the X-ray tube. So now, when the machine is turned on, immediately when you get into the lab, you turn the machine on, the X-ray tube emits a focused beam, a collimated, collimated light, or collimated X-ray beam. All right. So I told you that the collimated, it means the beam that is focused. Now, so when the machine is turned on, like I mentioned, the X-ray tube would emit a focused beam of X-rays towards what? Towards these are the collimated, the focused beam of X-rays towards the towards the sample. Now, these X-rays have a very short wavelength, similar to the distance between the atoms in a crystal, making them ideal for studying crystal structures. I've already mentioned that if we've got some atoms, then we'd have this plane, and then this distance is d. All right, is the distance between the atoms in a crystal. All right. So now the X-rays, these X-ray beams, as they are traveling like this, they'll be traveling like that. Never mind my drawing, good people. But now we've learned that, for example, the distance from here to there, it makes one wave. So this would be what we call the wavelength, or the distance from here to there, like that, So this is what you call there. It's what you call the wavelength. So the wavelength, or the short wavelength of these the beams of these X-ray beams, it's similar to the distance d between the atomic planes. That is one thing I want to for you to keep in mind. All right. Now we also have the special thing called a sample holder. Okay, within this machine, the sample holder. Now, the sample holder, you would agree with me that it's where you place the mineral sample you want to study. All right, it's where you put the mineral sample you want to study, and then this holder. So this holder it's carefully positioned in the center. This holder is carefully positioned in the center, like here. Can you now see? It's carefully positioned in the center of the machine, so that now the X-rays can shine directly on this sample. All right. So when it's at the center, the focused beam or the collimated beams, X-ray beams will shine directly on this sample. All right. Now, the sample is usually in a powdered form, which ensures that the X-rays can interact with the crystal from multiple angles. All right. Like I said, if you haven't yet visited the video on X-ray sample preparation, the powdered samples, you are more than welcome to visit that. But now, we want this sample to be in a powdered form. This powdered form, it allows the X-rays to have a good interaction with the crystal, okay, from multiple angles. All right. And then we also have this portion. We also have this portion over here. We call it a goniometer. All right. So the goniometer, it ensures that the X-ray tubes and the detector, the X-ray tube, all right, and the detector move in a what you call in a synchronized fashion around the sample. All right. But to not confuse you, especially this goniometer, it ensures that now this detector and the sample, all right, they move. Okay, so let's say you were to take this one over here. Now let's say you were to take this detector over here. Now this sample holder will be somewhere in this fashion. Okay, will be somewhere in this fashion, something like that. So now this movement of a detector, it tampers with what you call the angle 2D, and then it allows the sample to be analyzed in different angles, okay, or in multiple angles. All right. So yes, then we also have what you call a detector. Okay, we have what you call a detector, and it's self-explanatory, because a detector, its job is to agree the X-rays that hit the atomic planes within the crystal. They get to be scattered. Can you see these focused X-ray beams that hit the atomic planes? They get to they get to be scattered in different directions. They get to be scattered in different directions. Now, so the function of a detector is to detect or is to pick up the scattered X-rays, is to pick up these scattered X-rays and record the intensity and angle of each scattered wave. So you'd have this one, and then you'd have the intensity, and then which is what would behave in those graphs. All right, and then you'll see this on your computer. You'll see this on your computer. So that's that. All right. So sorry about that. Let me quickly clean this one. All right. Yeah, so basically that's the components that you would need to understand. All right. So moving right on, we wanna understand the operation now, how this XRD operates. All right. So in 1912, the Max von Leu discovered that the crystal can act like three-dimensional diffraction gratings for X-rays with wavelength similar to the spacing between the planes in a crystal lattice. I've already explained that the distance d, it's similar to the wavelength of the X-ray beam, and then that distance d is the distance between what you call the atomic planes. All right. So the discovery led to the X-ray diffraction becoming a widely used method for studying crystal structures and atomic spacing. All right. It was widely used because of the understanding of the wavelength being similar to the spacing d. All right. So I hope it makes sense. All right. So you now agree with me that if you have an X-ray diffractometer, okay, so the setup in itself, it has been designed so that the sample is rotated in the path of focused ray beam at a specific angle. All right. So I've already explained that this setup, it has been designed in such a way that the focused X-ray beam or the setup has been designed in such a way that the sample is rotated. I've showed you how the sample is rotated, but now in the path of focused X-ray beam at a specific angle. Now, if you keep on rotating this detector, even the sample, it's being rotated. So when the sample is rotated, it will always be rotated in the path of a focused ray beam at a specific angle called theta. All right. So called theta, this angle or incident angle. So at the same time, the X-ray detector, which is attached to the arm, the X-ray detector, detector, which is attached to an arm, moves to catch the X-rays that have bounced off the sample. The aim of the detector is to always catch the X-rays that bounce off from the sample. So this detector rotates at an angle of 2 theta. So can you now see this? It rotates at an angle of 2 theta. So the device that controls the angles and rotates the sample is called the goniometer. All right. I've already mentioned that to you, that it's what you call the goniometer. It allows the detector and the sample to now be rotated. Okay. So I hope this makes a bit of a sense. So now, having kept that in mind, that X-rays are focused into a straight, narrow beam and aimed at the sample. Now, you would agree with me that both the sample and the detector, when they rotate, the detector measures the intensity of the X-rays that bounce off the sample. All right. So now, when the angle of the incoming X-rays matches the conditions of Bragg's equations, the X-rays align perfectly. All right, causing a strong signal or peak to be detected. All right, which is why I'm gonna explain what you call the Bragg's law. All right. So X-ray diffraction works by using the constructive interference of monochromatic light. All right. So let's refresh our minds. We know from physics that the monochromatic light refers to the light that consists of a single wavelength, or you might say color. Okay, so this in simple terms, it means all the light waves have the same frequency and energy, resulting in a uniform and pure color. So in scientific experiments, for example, such as from XRD, all right, monochromatic light per se, it's often used to ensure that measurements are accurate and consistent. Because this monochromatic light, it reduces the interference and simplifies the analysis of how the light interacts with the material being studied. All right. So I hope you understand what monochromatic light is and why is it important. All right. So the X-rays are generated by a cathode ray tube, filtered. All right, filtered to ensure they are monochromatic. All right, because this monochromatic light, it's very important because it reduces the interference and simplifies the analysis. All right. So it makes sure that the measurements are accurate and consistent. All right. So this X-ray cathode, it will filter now some of the beams. Now ensure that now the beams are collimated or are focused. Okay, so they are focused into a narrow beam, and they then detected then directed at the sample. So when these X-rays hit the sample, they interact with the crystal's atomic planes, as I've explained. If the conditions meet Bragg's law, all right, following this formula, the X-rays will constructively interfere, creating a diffracted ray. So I'll explain to you this Bragg's law and also what we mean when we say if the X-rays get to constructively interfere. But now, for example, we know that when, for example, if you have, I'm not good with drawings, but let me try my level. But something like this one. I'm bad. I'm really bad. Let me try. Okay, then let me do this. Okay, better. Yeah. So we know now that these things, they will cancel each other out, and then we would have a straight line. All right, would have a straight line because they are distracted. They are what you call the destructive interference. But for example, if these things, they are like that, then they will cause um, 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 the what you call the constructive interference. So when the X-rays, they interfere, all right, they interfere in such a way that they align themselves perfectly. They cause what you call the constructive interference, and then this thing, it's the one that helps the detector to be able to detect the X-ray beams, all right, and then forms high intensities. All right. So this, it now follows what you call the Bragg's law. All right. So I've already mentioned the fact that we have got the distance d, which is the distance between the atomic planes, and then we know that we have got what you call an atom. So we know the atom, it consists of the nucleus, which holds the protons and neutrons. All right, and then we've got the electrons that are surrounding the nucleus. And then so the X-rays, what happens, good people, is the X-ray beams, when they hit the atom, all right, now the electrons, they become energized, all right, they absorb this X-ray energy, all right, but now they end up, what they end up doing is they end up not using this energy, and then they will re-emit this X-ray. All right, basically that's how the atom behaves. All right, now, so understanding this, all right, so let's say this is that X-ray tube over here. and then it has some filters, and then it allows the monochromatic light go in that direction, and we know we've got the wavelength. We've got the wavelength, and the wavelength is the same as the distance d, isn't it? Now this, it will go into a sample, all right? It will go into the sample, hit the sample, all right? Now, I want to explain specifically when this hits when this light hits the sample. So what happens is, also, or what is happening is, let's focus specifically here, all right? For example, I want to use this one. I can use this, let me try to draw it. Okay, how can I draw it? It's not gonna be nice, but let me try to use this one, for example. So let me try to use this one. Let's say, yes. And then this is 90 degrees. And then this will be your angle theta. And then, sharp. This is your angle theta. Now, you'll always agree with me that, oh, this is distance d, this is distance d, and then the distance d, it's always the longer side. All right, it's always the longer side because of it's the atomic distance. All right. Now, but what's happening is the relationship between the diffraction angle and the spacing between the diffraction angle and the spacing between the atoms is given by Bragg's law. So I wanna show you how the formula has been created. Okay, so this is because the exact angle at which diffraction occurs, okay, can be determined by this triangle. Okay, but one thing we wanna bring to attention is the half the angle will be the half the angle half the angle will be of the incident, or then another half the angle will be of the diffraction. So the half the angle between the incident and scattered beams. All right, so now it will mean this will be how do we sorry, not angle, sorry, not angle, but this wavelength. All right, so half the wavelength will be from the incident and half the wavelength will be from the diffraction, so that they make complete one wavelength. All right, they make a complete one wavelength. So having to understand that, now here we having half the wavelength. All right, so let me redraw it over here. Sorry about that. So we have half this wavelength, so like that. Then we have the angle theta, and then we have got the distance d. But we know from soccer tour, okay, that the sine theta is the opposite, which is half divided by the distance d. So playing with your math, you'll agree with me that this is the same as your multiply by 1 over d, which is just 2d sine theta. So this now you end up having 2d. If you multiply both sides by 2d, you end up having 2d sine theta is equals to n that. All right, so now which is why Bragg's formula, okay, it's in the form of 2d sine theta. All right, so which is why the Bragg's law connects the wavelength of the X-rays with the angle of diffraction, 2d. The angle of diffraction, it's the 2d. All right, because this angle between between the incident and the diffracted rays, it's what you call the 2D. So it's this one, 2D. So the Bragg's law connects the wavelength of the X-rays with the angle of diffraction and the spacing between the planes in the crystals. Okay, and this is the spacing between, or what you call the atomic spacing. All right. Yes. Okay. Or this the distance between the atomic planes. So that is what you call the Bragg's law. So the diffracted X-rays are then detected and processed and counted by detector. By rotating the sample through a range of 2 theta angle, the instrument can detect all possible diffraction directions. Okay, thanks to the random orientation of the powdered material. So showed you that if the more you rotate this detector, this detector can be rotated in this direction. And then if initially, if the sample was like this, then if you rotated, the detector is rotated to this point, at that point in time, it will be something like this. So you as you keep rotating the detector, the sample also get to be rotated, so that now this sample can be analyzed at different or multiple angles. Okay, so that you can have the representation of the data within the sample. All right. So yeah, and then thanks to the goniometer. All right. So by analyzing the pattern of peaks on the graph, this graph, okay. So it means as this detector and the samples are rotated, you get these peaks. You get to see these peaks on the computer. You get to see this kind of graph on the computer, the graph of 2 theta and the intensity. All right, you get to see this kind of graph. So these peaks, like I said, yes. So by analyzing the pattern of peaks on the graph, scientists can determine the crystal structure of the mineral, the position, and the intensity of peaks. Okay. The crystal structure of the mineral. So the position and intensity of peaks reveal how the atoms are arranged within the crystal, helping to identify the mineral and understand its properties. So by converting the diffraction peaks into d-spacing, okay, the scientists can identify minerals as each mineral has a unique set of d-spacing. Oh, each mineral has its d-spacing. Okay, they have got their own d-spacing. So if you were to compare the d-spacing of each mineral with the standard reference, all right, with the standard reference, then you'll be able to identify the minerals, okay, different minerals. So basically, that's how it works. All right. So I hope it makes sense. So I wanna emphasize the angle 2 theta. Okay. So in XRD, good people, 2 theta, it represents the angle between the incident X-ray, the angle between the incident X-ray, this one, and the scattered beam that is detected. So this angle is very important because it relates to the spacing between atomic planes, okay, according to that formula of the Bragg's law. So this angle is very important because it relates to the d-spacing and what you the d-spacing of the atomic planes in that crystal. All right. So then we have got also what we call powdered patterns. We have what you call the powdered pattern. So when a sample is in powdered form, all right, the tiny crystals in that powder are oriented randomly. Okay. So as the X-rays would now be interacting with this sample, as the X-rays will now be interacting with this sample. Remember, this sample has got some crystals, the tiny crystals that they are oriented randomly. So if now there is the interaction, the X-ray or the X-ray beam interacts with these tiny crystals, they produce a diffraction pattern that can be detected over a range of angles, usually from 5 to 70, or so as that as this detector it's rotated, as this detector the detector is rotated and the sample is rotated, then would have the interaction of X-rays with the tiny crystals. So they would produce now a diffraction pattern. These diffraction patterns, they can be detected over a range of angles, all right, producing these peaks. Okay, so usually, like I said, we have got approximately 5 to 70. Okay, so this angle. So what about this angle? This angle is very important because now during XRD experiment, for example, the data needs to be collected over a specific range of angles, not only one angle, but a specific range of angles. Okay, usually approximately 5 to 70 degrees. Okay, so this means that the detector is capturing how the X-rays are scattered by the sample over this range of angles. So this is important because different crystals and atomic planes will diffract the X-rays at different 2 theta angles. Okay, so they would diffract the they would diffract the X-rays at different 2 theta angles. So scanning over a wide range allows for a more complete analysis of the crystal structure. So you need this range of angles because now it will give you a complete analysis of the crystal structure. So which is why the rotation, okay, the goniometer, as it helps us rotate that detector and the sample, it helps us so that then we have got the complete analysis of the crystal structure. Okay, so I'm sure you are asking yourself, why this range? Why this range? Okay, this range of from approximately 5 to 70 is typical because it covers the most important diffraction peaks for main common materials. All right, so these peaks correspond to the distances between the atomic planes in the crystal, and analyzing them helps identify the material and understand its structure. All right, so which is why this angle 5 to 70, it's the normal one. Okay, normal one which covers the range of the materials. So it will give you sorry about that, it will give you the range of the or it will give you the complete analysis of the crystal structure. So I hope it makes sense. I think this brings us to the end of the XRD. Okay, the lesson on XRD. I hope you understand now what is an XRD, how the components of XRD, the kind of sample, the powdered sample of an XRD, and how it operates, and how the Bragg's law connects the wavelength of the X-rays with the angle of diffraction, and of course the spacing d. All right, and then I hope you understand now that each mineral has a specific spacing or d-spacings. So if we compare these d-spacings with the standard, okay, the frame of references, now we'll be able to understand the different minerals. All right, I hope this makes sense. So let me thank you guys for joining us or for tuning in today. Your support means a whole lot to us. Please don't forget to like, share, comment, and hit the notification button below so that you get notified once we upload new content. And I would always like to say, until next time, cheers.